give Andy a warm welcome. I know it'll be great to hear him speak.
Thank you. Thank you for that. Can you hear me all right? I don't know whether the mic's working all right. I don't know whether this is working. Oh, it's working. Good. Right, so thanks for having me. Just before I get started, can I just ask who knows what Conway's law is? Just put your hand up. Okay, cool. Just so I sort of know, you know, not to sort of either baffle you or patronise you. Okay, cool. So in the beginning of my time at Sky Betting and Gaming, which is about 4 years, which isn't really that long, when I joined, I remember not long after I joined, we had Grand National, which is the big event in the sporting calendar for Sky Betting and Gaming and all bookmakers. So Grand National, if anybody doesn't know what it is a huge horse race that happens once a year, and it's probably the most popular sporting event, well, it is the most popular sporting event in the UK in terms of bets. So at that time, I mean, I haven't actually got figures, but it was we had around about 60 bets a second was the kind of load that we were dealing with. Now, if you sort of roll forward to about 4 years later, we were handling, just check my number here, we're handling 350 bets a second in the space of 4 years, which is, you know, roughly a six-fold increase. And actually, when I first prepared this talk back in October last year, that's how far my graph goes up to. But actually, last week we had the Cheltenham Festival, which is another popular horse racing event, and we saw about 500 bets a second. So this graph is sort of continuing up in this incredible trend upwards. So this is a really interesting challenge for people working in IT, and consequently, to support that kind of growth, we needed more people. We needed more people in our software engineering team so that we could build systems that could handle that kind of load, and also, you know, remain competitive and build new features and so on. We're now the largest bookmaker in the UK by customer volume, not by revenue, unfortunately. But anyway, William Hill is still, our sponsors are still ahead of us on that one, despite buying the sandwiches. So we've scaled our technical teams quite dramatically over the last 4 years. We've tripled our engineering headcount, roughly. But of course, this scaling poses some interesting challenges for an organisation. One of the first ones being communication. Like, how do you align all of those people? So let's just sort of think about this mathematically for a minute. So imagine that you're a startup in someone's bedroom and you had 3 people in your company. Then the number of conversations you'd have to have, the number of interactions you'd need to know what everybody was up to would be 3. Yeah? And then let's imagine that you decided to hire another 3 people. And the number of interactions that you would need so that everybody knew what was going on would be 15. And at that point, I mean, that may or may not be surprising to you, but at that point I should say this is the formula that we're dealing with here, which is the number of people times, effectively, the number of people, divided by 2, right? Because once you've had a conversation with that person, they've already had a conversation with you as well. That's kind of how the formula works. And the reason I put it there, which will become important later, is that this is, for anyone mathematically minded, this means that we have something quadratic going on. So if you drew a graph of this, the graph goes like this. And this is why, if you sort of double the number of people again, you now have 66 interactions that you need in order to know what everyone's doing. And if you double that number again, then you actually have 276 conversations you need to have every day if you want to be completely on top of what everyone's doing. Now, that is a lot of people. I guess as we sort of scaled our teams, so, you know, when I joined, we had, I think it was 150 people in tech, at least in bet, the part of the business I work in. It's 2 parts, bet and gaming. I'm in the bet part, so I think about 150 people in tech. There's loads of communication going on. I remember when I joined, I was really struck by a number of conversations, whiteboard discussions, pair programming, mob programming. There's all sorts of stuff going on, and if you needed a decision on something, you need to figure something out, you just jump up and wander over and talk to that person. We're all on the, you know, all in the same area. It was quite easy. But that was 4 years ago. Now, at that time, I could interact with all the people I needed to get my job done, to make decisions, to figure out what was going on, and so could everybody else. It was sort of manageable. But of course, as I said, we've sort of scaled up, and now, just to go back to my formula before, anyone like to guess how many interactions you would need for 500 tech people if they were going to talk to everybody else and figure out what everybody else was doing? Want to hazard a guess at the number? Oh, what, you just blown it out of the water. No, it's only 124,750. Oh well, you spoiled it now. So yeah, I mean that seems like a really low number now, but there we go. So this is how many interactions you would need to have if you wanted to know what everybody else was doing. Now, obviously this kind of person-to-person interaction is just completely ridiculous, and this is why companies split things up into teams. That is why companies are structured into different departments and teams, because what you want to try and do is reduce this communication overhead. You want to split the company into groups where people within that group can operate relatively independently without needing to go and talk to all people all over the place all the time. So it's sort of, you break a company up along communication lines, or if you like, along groups that can be autonomous. So autonomy is not a controversial thing in that sense. But as you grow, you pay a bit of a cost, because whereas in a startup, you know what everybody else is doing, but you also, you bounce ideas off each other. You're quite aligned in what you believe, and what your values are, what your tech principles are, in what you're aiming to do, or what your tech strategy is, or your product strategy, or whatever. And this problem of sort of alignment diverging is similar, I think, to the evolution of species. So where geographical separation has occurred hundreds of thousands, or indeed millions of years ago, you start to see a divergement, that's a new word, in the how people evolve, and of course we see this with people as well. We see it with language as well. So wherever there's geographical separation, you start to see this divergence, there's the word. It also means that because of our sort of genetically programmed fear of difference, that we tend to talk less to people in other teams. Even if they're 5 meters away, you tend not to get off your chair and go and talk to them as much. And this is a big problem. This is a culture problem. And trying to maintain your kind of small company culture, and Sky Betting and Gaming is very proud of its culture, how you do that when you scale up rapidly is I think, a huge challenge. I really like this quote from Craig McLuckie at Heptio. I'll just give you a second to read it. Culture, I think, is crucially important for a company. I think if your culture isn't good, then what you produce won't be good. Customers won't like what you produce. If, for example, everyone's too busy to help each other, then you end up reinventing the wheel, you end up producing disjointed products, and actually it starts to become a crap place to work. And your best people, the ones who are most employable out on the job market, eventually they'll kind of swan off and go somewhere else. So, huge problem. Another problem that I think you start to experience with this scaling is around velocity. Certainly at Sky Betting and Gaming, we saw our velocity really drop. And this is as a result of contention. So as we tried to align on how we did things and created central teams sometimes, that central team became a bottleneck because you had to queue up to get work done by that team. That slowed things down. And I'll talk a lot more about this in a minute. And then another problem we started to see creeping in was around stability. So because we had so many people working on this monolithic web application that had previously served us very, very well, suddenly we were starting to see a very high rate of change in this area, which meant that we're getting more bugs cropping up, more regression risk, because it's all happening in the same code base. and also a larger blast radius. When something does go wrong, the whole application dies, the whole website went down. So that's just a sort of flavour of some of the challenges that you get as you scale as a company. So what I want to talk about is how Conway's law can help us. So this guy, Melvin Conway, wrote a paper in 1967 that has been sort of had various resurgences over the years. And one of the key things that he talks about in there is that we are constrained to build software systems that mirror the communication structures of our company. Now, a few years ago, does anyone follow the ThoughtWorks Tech Radar? Has anyone seen that? Put your hand up if you know the ThoughtWorks Tech Radar. So ThoughtWorks, quite a big software consultancy, they publish each year. Actually, I think they update it each quarter. Actually, you should know that. They publish what they see as the latest and greatest tech trends, essentially. And in one of the sort of quadrants of this radar, a few years ago, they put in something that they call the inverse Conway maneuver. And this was taking Conway's law and sort of turning it on its head and saying, maybe if we structure our company in the way that we want our software systems to be structured, then actually our software systems will follow suit. I think this is quite an interesting concept. It's trying to use that synergy between how we structure people systems and how we structure computer systems. And that's really what I want to talk about for sort of the bulk of this talk. So one of the things that we talk about, so I'm an architect for Skydet, so one of the things that I talk about quite a lot is this concept of decoupling. And I'm just going to spend a few minutes talking about what I mean by this. So I've already said that we structure a company into different teams or departments or possibly P&Ls in order to try and minimise this problem of communication. And each one of these things we want to operate fairly independently in a fairly decoupled way. So what does it mean to be decoupled? So this is a coupling scale I've drawn for you here. So when we say decoupled, often what we mean is we really mean loosely coupled, because if one system depends on another system, then there is some coupling, but it's trying to make that as loosely coupled as possible where that makes sense. So on this scale, at this end, we have a toilet that is tightly coupled to the plumbing system in my house, and I'm fine with that because the number of times that I need to move my toilet to a different room in the house is pretty rare, right? I don't change my sewage pipes around that much. It doesn't really affect me too much. On the other hand, if I want to plug in my mobile phone to charge it, if it was wired into the wall, that would be a real pain in the backside. So, you know, I quite like that I can just plug it in anywhere. And some of the ways that we achieve that, of course, are through things like, you know, this standard interface that we have here. So is tight coupling always bad? Because we talk a lot about loose coupling being good in software system design. But in the case of the toilet, like, no, it's not. Sometimes that's just the easiest thing to do. But there are plenty of times when tight coupling is pretty bad. So for example, if you have two systems that depend on each other, that have to be coupled in some way, then it becomes a big problem because when you change one, more often than not, you need to change the other one. And if it's hard to synchronize changing those things at the same time, then that can be a really big problem. It means that you go very slow, and it means there's a lot of risk involved. For example, if these two tightly coupled systems here are owned by different teams with their own roadmaps and their own priorities, that becomes a real headache. Similarly, if you have multiple tightly coupled clients, so here we've got a database schema, for example, that's being used for lots and lots of different use cases, lots and lots of different systems and teams are all sharing this database schema, and then imagine that you need to change the schema because some security thing has come along, or because, I don't know, you need a bigger number, so you've got to change the column size or the data type or something. You know, these systems, these changes become very, very difficult and very, very risky to do. Which is why, incidentally, you should never integrate systems using database schemas. If you want to reuse your system and it has a whole bunch of tightly coupled dependencies, then that becomes extremely difficult to do as well. For example, if you have an application where the environment config is actually like baked into your system, then it becomes very hard to deploy your system in different environments. Or if you spin up whole new environments, you've then got to make a code change. So this is why things like 12-factor talk about just separating that out. And similarly, if you want to be able to test this thing in isolation, then actually this bunch of tightly coupled dependencies means that becomes quite hard to do. So that was the reason why you don't want to tightly couple. Loose coupling is quite often the right thing to do. Has it got any drawbacks? Yes, of course it does. So one of them is consistency. So if we think about loosely coupled teams, for example, decoupled teams operating independently, then the chances are they might solve the same problem in different ways. So at a company level, that's quite inefficient. And I guess it also might have some issues around being able to move people between teams. You can't do that as easily because they've got to learn a whole bunch of different stuff. It might also be a headache if you've ever been involved in a company-wide audit, and God knows if you work for a betting company, you get involved in a lot of audits, then sitting down with an auditor and them saying, what's your approach to, I don't know, access control to hosts? And he said, well, it's funny you should say that. We have a standard. In fact, we have 17 different standards. Let me talk you through them. It becomes more difficult to do that stuff. Then at a sort of macro level, overall system complexity can go up. So this is the journey that Sky Bet, particularly Bet, has been going on for some time now, where I mentioned before this sort of monolithic application that we had, and how we're trying to split things out into a more microservices approach. So this is nice because each of these stacks here is independent, it can evolve independently, but when you look at the complexity of these things next to each other, actually you've got a lot more things on the right-hand side there that you've got to worry about. So the complexity of your system definitely goes up at a macro level. You might also get reduced performance as well. So whereas previously in our monolithic application, everything was happening in process, it was super quick. But now we've started to separate things out and we have a distributed application, then actually now you've got remote network calls, which are orders of magnitude slower. It might be harder to debug your system as well. A typical approach in decoupled architectures is to use asynchronous messaging in pub/sub. But actually, those kind of systems are very, very hard to reason about. The number of states the system can be in is far more than you can understand, reason about. It becomes very hard to reproduce issues in a system like this. So given all of those problems, why at Sky Betting and Gaming and lots of other companies do we want to decouple things? So number one, we're growing fast, as I said. We want to be able to horizontally add teams to build new features, and we want to be able to do that without contention. We want to be able to constrain blast radius. So if this thing blows up, then we've only got one part of the site that blows up. And similarly, if there's a bug in one part of the site, then there's only one part affected. We want an evolvable architecture as our company evolves. And having lots of decoupled things is good because small, simple things are easier to change than big, complex things. It means we can go faster. And briefly, in systems design, how do we do that? Well, anyone technical in the room, I guess, will know well-defined versioned interfaces, like the plug socket. Canonical data schemas can help. Separate deployment pipelines so that you're not contended waiting for other teams. Separate infrastructure, again, to minimize blast radius and also separate out your load profiles. Dynamic binding, by which I mean things like service discovery and dependency injection, so that you can focus on your application code. Asynchronous messaging, I've already mentioned. Functional design can help as well, can help to guide people into building independent units that are by nature decoupled from other things and easy to test in isolation. And then this idea of choreography being better than orchestration. And this is something that, again, ThoughtWorks talk about in their book by Neil Ford and the others, Rebecca Parsons and somebody else. I'm getting old, can't remember. So their book around sort of continuous architecture, architecture evolution, these concepts, they talk a lot about choreography. So what do I mean by choreography? So let's talk a bit about that. So this is the second of these sort of software systems things that we can learn from, I think, in organisation design. So it often feels easier to build a software system in a way that has a sort of central controller. So, for example, think about a piece of code like this. It's very easy, I think, to understand what this piece of code is doing. It's therefore quite easy to debug, it's quite easy to refactor, it's quite easy to maintain. So that's quite good. However, it also probably implies what might be an undesirable coupling going on here, because this piece of code here, this system here, let's imagine that it runs on one machine and it's calling out to a bunch of other services. It means that as you scale those things out, you've got to scale your controller as well. It means that if your controller breaks, all those systems break. And also, it has a dramatic effect on the performance of your system, as I'll talk about in a little while. And I suppose one other thing to point out is that if you want all of these things to happen in an atomic way, i.e. you want to guarantee an ACID transaction around these things, i.e. you don't want a couple of these things to happen and the other ones not to, and end up with an inconsistent situation, then you might need to wrap this in a transaction. And distributed transactions are really, really hard, and also very slow as well, that hurt your performance. So this sort of model of the central controller can be quite problematic. So think instead about something much better. Choreography. And I don't think anybody would deny that this is much better than anything I've put up so far. So in choreography, the concept is that instead of needing the conductor at the front, orchestrating things and making sure that things happen at the right time in the right order, actually, before then, before showtime, you've actually already agreed what everyone's going to do. So in software systems, this means configuring all of your software components and services in such a way that they can operate independently. Reactive programming, event-driven architectures. So what you do is you define what the components should do, and you define what their dependencies are, and then, as I mentioned with the dynamic binding, perhaps the dependencies are supplied to that service at runtime by the platform that it runs on. Maybe it uses Console for service discovery, or maybe it uses Kubernetes to provide it with the network layer and things like that. So now our program looks a bit more like this. So what I'm envisaging here is some kind of pub sub, an event-driven architecture where when we process the order, we just put a thing on a queue and we're done. And then we let all of those choreographed, independent things, whatever they may be, just do their thing with that event. They all know what to do. They're going to process this event. So the email sender program is going to do its thing, and the order store processing thing is going to make a note of it, and fulfillment is going to happen, and so on. So what we have here is loose coupling, just by introducing this asynchronous messaging here. Be that however you do that, RabbitMQ or ActiveMQ or Kafka or whatever it might be. Now, that means that these things on the right-hand side, because they've been choreographed, it also means they're autonomous. So let's think a bit about teams. So at Sky Betting and Gaming, we say we want autonomous teams. But what does autonomy even mean? Because we use this word a lot. In fact, it's a little bit overused. Has anyone come across the Dan Pink's thing about what motivates people? Autonomy, mastery, and purpose. If you can give those three things to somebody, then they're quite motivated. In other words, they're autonomous, so they have control over what they work on. Mastery, meaning that they have the skills that they need to do it. And purpose, they have a clear goal that they're aiming for. And if you have those three things, you feel quite fulfilled and motivated in your work. And another question for you. Has anybody ever heard of this thing called vMost? Just put your hand up if you're familiar with vMost. Okay, so for anybody that's not familiar with it, very briefly, the idea being that you have a sort of, down the bottom here, you have a lot more detail, sort of immediate near-term tasks that you're going to do. And you're doing those tasks probably in the software teams with the things they're delivering. You're doing those in order to try and achieve your strategy. And you might have a number of strategies across the company. And those strategies all sort of add up in order to achieve the company's objectives that are defined by another level of management or leadership above that probably. And then above that you might have a mission statement. And then you might, at the very top there, have a sort of company vision, which is often something like, we want to be number one in our market, something like that. There's lots of different approaches to this. Companies do this in different ways. But this is a common way of doing things. Now, typically our development teams, in Skybet we call these squads, typically these development teams operate sort of down at this level. And I would argue that actually we'd be much better off if those development teams operated more at this level, i.e. we include some of the people who are good at coming up with strategy, if we actually have them working as part of the team. I don't mean writing code necessarily, but working with the team very, very closely. And this is what I'm talking about with autonomy. I don't mean that, a team down here sets their own vision, mission, objective. That would be madness. And some of you might have seen this before. So this is something that Spotify put out some years ago by a guy called Henrik Nyberg, who worked for them at the time. And I think this is a fascinating way of thinking about autonomy. And what it's saying is autonomy is important, but it's a nightmare if you don't also have alignment. So just briefly walk you through this if you haven't seen it before. So down the bottom here, we have low autonomy and low alignment. You've probably got micromanaging, and people don't really know what they're working on. Those three things are autonomy, mastery, and purpose. They're completely lacking the autonomy and the purpose. They're just drifting around doing whatever they want. They don't really know what they're supposed to be doing. What you see in a lot of companies up here is where the company believes that IT is a function. For anybody that's read A Seat at the Table, if anyone's read that book. A lot of IT organisations, particularly historically, believe that IT is a function, is a thing that needs to be controlled. So it needs rigid processes, it needs signed off requirements documents and deadlines and plans and waterfall delivery typically. So you have quite an authoritative organisation and a conformist culture where you do what you're told or else. And we've got the pointy-haired boss there from Dilbert kind of saying, we need to cross the river, build a bridge, go do it. Down here, we've got high autonomy. So we said, yeah, squads, you're autonomous. You make your own decisions. You do whatever you think's best. And that's kind of chaos. And you've got the boss thinking, God, I hope someone's working on that problem. But you're not achieving the company goals. So obviously the nirvana is that top right, where the pointy-haired boss is saying, we need to cross the river. That's my company objective. Figure out how. And we're empowering that team to do it, to make the decisions they need to make to achieve those goals. And that doesn't mean just taking a bunch of software engineers going, sorry, I'm responsible for what? It means putting people who are good at that stuff into the team and working with them. Right, so I've just got a couple more things to talk about. So one of them is this thing called the universal scalability law that I think is quite interesting in this space. So I mentioned that one of the problems that we have as we scale is around velocity going down. In other words, and by velocity, essentially I mean the throughput of my company. So again, this sort of analogy between systems and companies. So universal scalability law is something that is really about software systems and has a wide variety of applications, hence the word universal. It can be used in the design of your networks, in disk arrays. There's all sorts of ways in which this thing holds, and I believe it holds for people as well, people systems. And there's an excellent blog post about it by Adrian Collier that I highly recommend you check out, which a lot of this stuff is borrowed from. So, the universal scalability law. So this was created by a guy called Gunther, I've forgotten his first name, and his paper talks about thinking about as you apply additional load to a system, and hence you apply additional workers, if you like, additional systems to handle that load, what is the throughput that you can expect from that system? And the ideal case is this. As you add more things to do the work, then you get increased throughput, and you have a linear relationship between those two things. And this is the formula that governs that. In this formula, the C there is capacity, or throughput, and the N is the number of workers, the number of nodes, the number of systems, whatever you want to think of it as. And that divided by 1 obviously is irrelevant here, but that will become important in a second when we talk about, my slide moves on, too far. I'm sorry to put formulae up, by the way, for anybody who's not keen on formulae. What this formula now introduces is the idea of contention, and that's what this alpha symbol here is representing. So you remember I said about having the central team that we were waiting on to get our stuff done. The effect of contention, which in systems designs is about the effect of having to queue for a system to respond to you before you can continue to do the work you're meant to be doing, is this. So this alpha coefficient, it varies between 0 and 1. So you can see that where you have no contention, alpha is 0, it essentially wipes out this bit here, and you're back to that formula I showed you before, the linear scalability, which is perfect and shown in the red dotted line there. And actually, sorry, the legend's dropped off the bottom there, but as we increase load on the system, or as we increase the number of people in our organisation, then if we have contention, like I was talking about, actually we start to do this, and we sort of plateau. And it means that adding X number of people initially has quite a good impact on throughput, but then as you scale your company even bigger, adding the same number of people has a much smaller impact on throughput. So contention is a big problem. As I say, it means waiting for other people to do stuff, waiting for other teams. It could be something to do with if you have managers or leaders involved in decisions at a level of detail that they shouldn't be involved in. Now, just put your hand up if you think that's a problem that you might have in your organisation. A few people, yeah. So we definitely still have that problem. But the situation gets even worse when you consider, I know it's a weird looking graph, when we consider this extra coefficient here, this is nearly the last formula, I promise, which is this beta coefficient, and this represents the cost of coherence. Coherence, defined by Gunther as the delay for data to become consistent. Well, in people systems, we can think about that in terms of the number of people involved in making a decision, right? Now, the effect here, that n times n minus 1 might look familiar to you from when I was showing you the stuff about the interactions between people. This is a quadratic relationship, and hence, this is why you see this green curve here, which is quite alarming, because it's just as bad as contention, really, at first, and then it gets a bit worse than the contention problem, but then, actually, we've added more people, and our throughput has actually gone down. That is how bad this problem is. So that is the problem that companies experience when you have a large number of stakeholders involved in every decision. Operationally, that kills your organisation. So now let's talk a bit about, oh, I've just pressed stop. Didn't know I could do that. So let's just talk briefly about Little's Law. So Little's Law is it's another systems concept which shows you the relationship between the wait time for your system, for your process, versus the amount of work in progress. So the number of tasks that system is trying to fulfill, and how that relates to throughput. So let me give you an example, like a people-based example for this. So let's imagine that you have the luxury in your company of working on one thing at a time. That'd be nice, wouldn't it? So if you work at one thing at a time, let's imagine that in a given week you get through maybe a couple of things. On average, those things take like 2.5 days. So you get through a couple of things a week. So your throughput is two things a week. And your work in progress is 1, because you're focusing on one thing. So that means that the wait time that anybody depending on you for a piece of work is roughly half a week. Yeah, that's not too bad. But actually, in reality, you don't just work on one thing at a time, do you? In reality, you typically work on, I don't know, maybe 20 things at a time, realistically. And so when you consider that against your throughput of 2 things a week, then actually that factors out 20 divided by 2. That means that people might expect to wait 10 weeks to get something from you. Now, of course, I'm using very rigid numbers, but you get the gist of it. Now, if we get a bit more complex about this, there's a thing called Kingman's formula, which a guy called John Kingman came up with, which builds on Little's Law, and it starts to introduce this concept of variability, because in reality, pieces of work don't take 2.5 days each to do. They vary massively, and some things take you 10 minutes. Some things might take you days and days to achieve. And I suppose the other thing is the rate at which work arrives varies as well. So the formula, sometimes called the VUT formula, takes all of those things into account, and the U is utilisation. So this graph is 3 arbitrary systems showing what happens to those systems as the utilisation of the system goes up. And what we find is that we have this exponential problem. Now, I haven't included the formula because I thought you might have had enough of formulas, and also it's too big and complicated for me to probably even explain it properly. But this is an interesting one, because what this means is if you are working flat out every hour of the day, working at weekends, really sort of trying to help people out when people come and ask you for help, you're saying, yeah, I'll help you with that, you're getting involved in lots of stuff. Your 100% or near 100% utilisation is actually creating this massive queue time. It's actually meaning that overall things grind to a snail's pace if everybody's doing that. And the sweet spot is probably somewhere around here, probably around 60% utilisation, let's say, where actually you're getting some really good, you haven't increased the time in the queue, but you're getting through quite a lot of work. So, choreography for computer systems. I'm just going to sort of try and wrap this up a little bit now. So choreography for computer systems means that we don't have a centralised controller. We've decoupled things out. So we've reduced the contention that I talked about before. It means that those systems can operate independently. We can scale them horizontally, and they sort of have resilience built in. In people systems, a lot of the same things are true. So if leaders stop being involved in the detail of every operational decision, then actually you reduce that contention. It means you don't have the micromanagement that you did before. And it means that the whole system can move faster as a result. Leaders can focus on, setting goals, direction, and structuring teams and processes. This is all choreography, right? So in other words, they're doing the choreographic stuff to make sure that when it comes to actually building the things at runtime, we can move efficiently. So in summary, going back to our vMost, these are some of the people that are responsible for some of these levels in the vMost. And let's imagine that these are our software teams down the bottom here. Obviously, we need our delivery teams to be talking to each other to get that alignment. Saying, hey, we built this thing, this might be useful for you. They're figuring out standard ways of doing things, best practices, all that stuff. And obviously, you need this kind of communication to be going on to make sure that the teams understand what the strategy is, like what's the purpose of what they're doing, because that will guide the decisions that they make every day. So there's lots of communication there as well. And of course, this happens throughout the whole company, right? We need this alignment to be going on. And this is choreography. I am not talking about day-to-day decision-making. What I'm talking about is alignment. So people making sure that they have the same sets of values and principles and standards and goals, so that when they do actually then operationally go and build things, they're doing it right. Now, of course, that person-to-person communication isn't the only communication we have. We have pub/sub in the human world as well. We have email, we have Slack, we have big meetings where everyone gets together and they put up slides and say, this is our strategy for the next 3 years, or whatever it might be. And we have a bunch of other ways of achieving alignment in an efficient way. But then all of this is the choreography. All of this is, to go back to the software systems analogy, this is your architecture. This is your systems design. Operationally, sad that that's off the bottom there, but operationally what we need is teams like this to be autonomous. And incidentally, something I didn't mention before is we do need those teams to be accountable as well. That is a really, really key thing of autonomy. Don't try and do autonomy without accountability and alignment. So I guess it's the 3 A's. Maybe I should copyright that. So just to sort of hammer home that point, this is the difference between architectural considerations and operational considerations. All these red arrows, you don't want that happening at runtime. You don't want to have all of those conversations at runtime and involve 1 million decision makers to get something done. That would be horrendous. What you need is for these people to be able to make decisions based on the alignment that's already happened. And that's it. Thank you very much.